Okay, so in this video, I want to talk about two special types of subspaces that are related to linear transformations. And so remember, with a linear transformation, if we have T from Rn to Rm, then we have associated with this an M by N matrix A. And so here I have T of X would be equal to A times X, again because T is linear. All right, so I'm going to define these special subspaces in terms of this associated matrix A. So, definition, let A be an M by N matrix. Then I'm going to define something called the column space. So we'll say the column space of a matrix A, denoted col of A, is the set of all linear combinations of the columns of A. And so, for example, if A is equal to this matrix, A1, A2, up to AN, with each column in Rm, then I can say the column space of A is just equal to the span of A1 through AN. And the proof of this is was basically outlined in class when we were arguing that the span of two vectors, or all linear combinations of two vectors, was a subspace of Rn. In that instance here, this column space is a subspace of Rm. And again, this was when Andrew commented, well, doesn't that sort of generalize? Can't you always do that? And the answer is yes. So again, a span of any set of vectors or any set of linear combinations of vectors is a space. And so this one that we're interested in for a given matrix is the column space. And we'll say this is a subspace of Rm, since each vector or each column has dimension m. Okay, and the second type of space I want to define is what's called the null space. The null space of a matrix A, denoted null of A, is the set of all solutions of the homogeneous equation A times X equals 0. And so we've also talked about this set on a previous handout. I said it's referred to also as the kernel. And so this null space is equal to the kernel, and I'm going to claim that this is a subspace. So theorem, the null space of an m by n matrix is a subspace of Rn. All right, so first I need to show that that this satisfies the three properties of being a subspace. So first, I need to show that the 0 vector is in the null space of my matrix A. And so to do that, I just need to check that A times the 0 vector is equal to 0, and yes, this is true, and so 0 is in the null space. Okay, the second thing I need to check is that if two vectors u and v are in the null space, then u plus v is also in the null space. Okay, so for that, let me first suppose u and v. U is in the null space of A, and v is in the null space of A. Then A times u is equal to the 0 vector, and A times v is also equal to the 0 vector. And so now I just need to check that A times u plus v is equal to 0. But we know by properties of matrix multiplication that this is equal to A times u plus A times v, which we know by definition of u and v being in the null space. This is equal to 0 plus 0, 0 vector, sorry. And so this implies that u plus v is in the null space of A. Okay, and lastly, we have this third property. If u is in, that looks like T, is in null A, and C is in R, then C times U is also in the null space, which means A times C times U is equal to 0. And so if we do that, we can check. So we get that A times C times U, again using the commutativity property of scalars, this is equal to C times A times U, which is equal to C times the 0 vector, which is equal to the 0 vector. And so since all three properties of the subspace definition are satisfied, the null space of A is a subspace of, and then again in this instance, it's Rn since my matrix had n columns. Okay, and the last thing I want to define is what's called a basis for a subspace, which I have alluded to in class, but I want to formally define it now. So we'll say that a basis for a subspace H of Rn is a linearly independent set of or a linearly independent set in H, so set of vectors in H that spans H of vectors. Okay, and so for example, if I had, say this was my matrix 1, 0, 0, 2, 0, 0, 0, 5, 0, then my column space, this was equal to, let's say, B, then my column space of B would be equal to the span of 1, 0, 0, 2, 0, 0, and 0, 5, 0. But notice, so, and this would be a space, it's the set of all linear combinations of these three columns. But notice column 1 and column 2 are clearly linearly dependent because column 2 is a multiple of column 1. So here, a basis for the column space of B would actually be the set of vectors maybe just 0, 1, 0, 0 and 0, 5, 0 because these two are linearly independent, and I'm going to claim that column space of B is equal to the span of these two vectors. Let's call this B1 and maybe this B3 since it's the third column. Okay, and so I'll leave it as an exercise to show that any linear combination of these two vectors that anything that's can be written as a linear combination of these two vectors can also be written as a linear combination of these three and vice versa. So it turns out that the column space can actually be represented by both sets, and since this is smaller and these two are linearly independent, then these two form the basis, whereas the three above do not. Okay, and lastly, I want to leave everyone with an example that we are going to work out together in class, but in case anyone wants to get a head start practicing with these concepts or these definitions, I'll leave them. So I'm going to let A equal this matrix 1 minus 4 minus 3 minus 3, 6, 7 minus 4 minus 2, 6. And I'll let the vector B be equal to 3, 3 minus 4. And I'm going to ask the following questions. So first, is B in the column space of A? And second, what is the null space of A? And third, do the columns of A form a basis for the column space of A?